Hi everyone. So in this video, we're going to go through the concept of a subspace of a general vector space. And the main aim of this video is to just show you how to determine whether something is a subspace or whether it is not. And so to do this, let's first take a look at the definition and then go through some examples. So a subset W of a vector space V is called a subspace if it satisfies these two conditions over here. And so this first condition is called closure under vector addition. And what does it say? It just says that if you take any two vectors in W, when you add them, you again end up with a vector in W. And that's why it's called closure under vector addition. The second property here is quite similar. It just says that if you take any vector x in W and you scalar multiply it, then you end up with a vector in W. Okay, so that's the definition of a subspace, and so let's take a look at our first example here, which is going to be a straight line which passes through the origin. So the vector space here that we're dealing with is just V, and it's the two-dimensional Euclidean space. And the vectors that we're going to form, that are going to form W, are going to be all vectors which lie on this yellow line here, which is just a general straight line passing through the origin. So let's give W just a bit more of a formal description. W is the set of all vectors, two-dimensional vectors, such that the second component is equal to m times the first component. And this is, what we claim is that this is a subspace of our vector space. And we need to show this. So how would we show this? Well, we need to show that W satisfies these two properties. So to show that it satisfies one, what do we need to show? We need to show that if we take any two vectors and we add them, any two vectors in W, when we add them, we end up with a vector in W. So we need to begin by having any two vectors in W. So what do we do? We say let x be a general two-dimensional vector, and also the same thing for y. So these are just two general vectors, and we're going to suppose that these are vectors in W. And then we need to add them and conclude that that vector is in W. But before doing that, these two vectors being in W means something. What does it mean? It means that the second component of each, in this case x, the second component of x, in other words x2, is equal to m times x1. But also the same thing is true for y. y2 here is just equal to m times x1, y1. Okay. Now that we have all of our information, let's try and make our conclusion. If we take x plus y, then this is just x1 comma x2 plus y1 comma y2, and this is just equal to x1 by how we add vectors in R2. This is x1 plus y1, and then x2 plus y2. And now we need to check, is the second component m times the first component? So let's check. If I take m times x1 plus y1, that's the second component of x1, x plus y. Well, this is just algebraically equal to this. And then by our assumptions here, we can replace each of these terms by x2 and y1. And so we get here the second component, x2 plus y2. So in other words, the first component times m is equal to the second component. And this is just to say that our original vector x plus y is in W. Okay, good. So that shows us closure under vector addition, the first property. The second property is actually very similar, and let's just quickly run through that. So the second property would say, again, what we need to do is just let x be a general two-dimensional vector, in W. Then, when we take the scalar multiple of x, we need to show that this is a vector in W. So k is equal to kx is just equal to kx1, kx2, and if I take m times the first component here, what do I get? Well, I can just now swap these two terms around and just get k times mx1. And again, by our assumption, what is our assumption? That this is a vector in W. In other words, this component is m times this one. In other words, x2 is m times x1. So what we get here is that this is just k times x2. And so what we've shown here again is that the second component here is m times the first component, so that this vector kx is going to be an element of W. And so that shows that these two properties hold here. In other words, any straight line which passes through the origin is going to be a subspace of R2. Okay, so that gives us our first example of a subspace, just a straight line through the origin. Let's take a look at some examples of subsets which are not subspaces. So here I'll give you two. So the claim is that these two sets represented by, so W represents the red areas in each of these sets, and the claim is that these are going to not be subspaces. And what is going to go wrong? Well, one of these properties here, one of these is going to fail. At least one, sorry. So which one in each case? Let's take a look. If I am here, if I am dealing with W here, what is W? It's the set of all these points. So this particular point, let's say here, this one, is going to be the point 1, 1. And the next point here, this is going to be 2, 2. And for instance, this point over here is just going to be 3, 0. And what is in common to all of these points is that they're all the vectors where the components are just integers. They're just whole numbers. Now, if I take two such vectors, if I take x and y in W, where x is just equal to x1, x2, and y is equal to y1 and y2, then when we add them, we just get this vector x1 plus y1 and x2 plus y2, right? Now, if we've assumed that x and y are in W, it means that this number and that number and this number and that number are all whole numbers. They're integers. And that means that if I add two integers, I get another integer. And when I add, so if I add x1 to y1, I get an integer. And if I add x2 to y2, I also get an integer. So in other words, x1 and x1 plus y1 and x2 plus y2 are integers. And so, in other words, i.e., this vector x plus y is an element of W. So actually, this is true. One holds for this set. So, okay, it's closed under vector addition. But what about scalar multiplication? So that's this property here. And it's going to be quite easy to see that this is going to fail. And how do we make a property like this fail? Well, we have to show that there is a particular vector. Remember, the statement says for any x, if I scalar multiply it, I again end up in W. So for any x in W, if I scalar multiply it, I get another vector in W. So to show that this is not true, I need to find a particular x and a particular scalar, k, which when I apply the scalar to the vector x, I'm not in W. So what we can do is show that if we set x, for instance, equal to just our vector 1, 1, this is definitely in W. And we can just set k equal to a half, for example. And then I'll just point out that x is an element of W here. But then when we scalar multiply them, when I take k times x, I get a half times 1, 1, which is a half, a half. And this is not an element of W. So what we've shown is that firstly x is in W, but a half x, or kx in other words, kx is not. And so what we've done here, what we've just done here is we've disproved this. This is not true. And so because both of the properties don't hold, this is not a subspace. Okay, good. So that shows you where 2 can fail and 1 can hold. Let's take a look at another example here quickly. And let's look at the subset given by this red region here on this side of the screen. So what is this? This is the set of all vectors x, y, where either one of the components, either x is 0 or y is 0. In other words, it's really just the axis here. It's all vectors which lie exactly on the axis here. Okay, that's what it means if one of the components is 0. Now, it actually turns out that for this particular vector space, we're going to this is going to be closed under scalar multiplication. So, for instance, if we take a vector x here, and if this was equal to, let's say, x, well, let's just say a0, for instance, then I can multiply this by any scalar, kx, and just get ka times ka comma k times 0, which is 0. And of course, this is an element of our vectors, of our subset W. And if we took if x had the only other possible form, in other words, it was equal to 0b for some b, then what we would get is that a very similar argument holds. K times x is just equal to 0 kb. And this is, of course, in W. Why? Just because one of the components is 0. That's why this is true. So in other words, if x was in W, then kx was in W. So what we've just kind of argued here a little bit informally is that property 2 holds. In other words, it's closed under scalar multiplication. So if I take a vector, let's say this one, and I scalar multiply it, I end up with a vector longer than it, like here, for example, or in the other direction. And so clearly that's showing you that a vector on the x-axis scalar multiplies to another vector on the x-axis. And similarly, if I look at a vector along the y-axis, if I scalar multiply it, I again end up with another vector on the y-axis. So property 2 definitely holds. Now, why does property 1 fail? To show that 1 fails, we have to give 2 examples of vectors which are in W, but when we add them, it's not in W. So let's let, for example, x be equal to 1, 0. So it's just going to be this vector over here. This is the vector 1, 0. And then let's let our vector y be equal to 0, 1. And which vector is this? Well, it's just this vector here. Okay. Now when I add them, when I add these 2 vectors, x plus y, I'm just going to get the vector 1, 1. It's very easy to see. And which vector is that? It's this vector, right? It's the vector. So if I look at, just complete the parallelogram, I get a vector from here to here. And clearly this vector does not lie in W, because why? Both of the components are not equal to 0. So what we've shown you here is that we have an x and a y which are in W, but x plus y is not in W. And it's really this here that shows that our property fails. This property fails. Okay, great. So we have given you an example of something that is a subspace, and here it gives you two examples of something that's not a subspace and how to show that it's not a subspace. Let's move on to another important example of subspace, and that is the example of a plane through the origin, a plane which contains the origin here. So what is our ambient vector space in this case? It's R3, three-dimensional Euclidean space. This plays the role of V. And what is a plane? Well, a plane which contains the origin is completely determined by what's called its normal vector here. And so that's what this vector is here. This is called the normal vector. The vector which is the unique vector, not unique, sorry, a vector which is perpendicular to every vector in the plane. That's how we can talk about planes. And the claim is that that the plane here determined by this normal vector is going to be a subspace. Okay, good. So in other words, this specific set P for plane, which is going to be the set of all vectors x in R3 which lie on this plane. And how do we say that, lie on this plane? Well, a very easy way to say that, my favorite way, is that x dot n is just equal to 0. Okay, what does that say? It just says that the vector x is perpendicular to n. And that's what we can mean. That's how we can talk about this plane here. Typically, another way of algebraically representing this is if you take the point x here, it's going to be in our plane if and only if ax plus by plus cz equals 0. But you will then just immediately see that this condition here is exactly this condition. Okay, good. So this is our plane, and we claim that this is a subspace. So let's first show that it's closed under vector addition. So we let x and y be vectors in P. And then let's ask the question if x plus y is in P. Well, then x plus y is in P. This is the same thing. This, by the way, just means equivalence. It means to say this is identical to say what I'm going to write here. And this is the same thing as saying that if I take x plus y, if I take this vector and I dot it with our normal vector, I should get 0. So if I can show that this is true, then I have shown that my vector x plus y is in W. All right, but so since x plus y dot n is just equal to x dot n plus y dot n, what are we getting here? Well, we're getting that this is just going to equal 0 plus 0. And why is that? Because we've assumed, I've said W, but I meant to say P. Sorry about that. But because we've assumed that x and y are elements of our plane, that means that these two dot products here are equal to 0, which is why we have the 0 plus 0 here. Okay, good. So since we have that this is 0, we have that property 1 holds. In other words, P is closed under vector addition. Okay, great. And in a very similar way, you can show that P is closed under scalar multiplication. Why? Because if I take x in P, so for 2, if I take x in P and I check what does it mean for kx to be in P, well, it just means that kx dot n is equal to 0. And this is going to be true because dot product will commute with scalar multiplication. In other words, this here is just equal to k times x dot n. And this is k times 0, which is just equal to 0. So since this is true, we have that this is true. And that shows you that what we've just shown here is that P is actually a subspace of our vector space. Okay, good. Let's move on to our last example here. So the last example comes from our theory of differential equations. So first thing to see is that, and this is really different from Euclidean space. So the set of all functions, smooth functions, functions which you can differentiate as much as you like, these form a vector space under which operations, just usual addition and usual scalar multiplication. Then what we call the solution space here, the subset of all functions which satisfy this condition, turns out to be a subspace. And why is that? Let's check why that's the case. Because if so just to be clear, what is W? W is equal to the set of all functions, I'll just say y. So the set of all functions such that y double prime plus y equals 0. Just so we will understand that y is a smooth function satisfying this equation here. And the claim is that this here is closed under vector addition and scalar multiplication. So in other words, if we take two functions in here, if we take y1 and y2 in W, then let's compute the derivative of the sum, and we add that to the sum as well. So what we're doing here is we're setting y equal to y1 plus y2, and we want to show that this y is an element of our space W, our set W. Okay, and the way that this works is you can see that because differentiation is linear, if I differentiate a sum, I can differentiate each component. It's the sum rule. And so we get here y1 double prime plus y2 double prime plus y1 plus y2. And this here is just equal to y1 double prime plus y1 plus y2 double prime plus y2. And now again, by our assumption here, this is equal to 0 and this is equal to 0. And so what we get is that this is just equal to 0. So I've just shown here that that W is closed under vector addition, and it's very easy to see that the similar kind of argument will work for scalar multiplication. So I'll just leave that to you. But what I would point out, which is quite interesting here, is that the order of this differential equation, so order 2 linear homogeneous differential equation, has kind of an interesting thing to say. And I'll just draw an analogy with R2. R2, how do we draw it? Well, not like that, but like this. It's the Cartesian plane, right? Every vector, it's identified with a point here, okay? But every vector, let's say xy, is a special linear combination of two vectors. This vector, which we usually call I, and this vector here, which is usually called j. And so what are these vectors? Exactly 1, 0. And here, just the vector 0, 1. And this x here is just equal to xi plus yj. And why do I say this? Well, these two vectors they form what's called the basis for our vector space, which you can see in another video. But the point is that every point in the space is going to be some linear combination of these. So every point, in this point, general point here, xy, it's just a linear combination of these two basis vectors. But something similar is happening for this particular space here. There's really two important solutions to this, this differential equation. I'm sure you can see that sine x and cos x are solutions. And if we draw an analogy here where we represent all solutions to our differential equation as coordinates in the plane, So in other words, a point here is going to be a function, right? And what function? It's going to be the function which I'm going to call this C1, and let's call this here C2. It's going to be the function which is the linear combination of cos x and sin x. And this point here, you can see, is so it's just this linear combination. And the reason I put it that way is because it can be obtained from these basic solutions, right? One of the important theory of linear differential equations is that if this represents cos x and this represents the sin x, then any solution to our differential equation is just a linear combination of these two. And so there's this interesting analogy between R2 and the solutions to this vector space. And I'll just leave you with what that general fact is. The general fact here is just that if you take the set of solutions to any nth order linear homogeneous differential equation, then it'll turn out that this is a subspace, and it's a subspace of dimension n. In other words, there are n basic solutions from which you can form every other solution by a linear combination. All right, that does it for this video, so I will see you next time. Thank you.